All right, great. Thank you for the introduction. Can everyone hear me all right?
Yes.
Yes, okay, thanks. So I'm Jake Shermeyer. I'm a research scientist at CosmiQ Works, and today I'm going to be talking about RarePlanes, which is both a data set and a research study that we conducted over really the past 2 years. And I'm going to walk you through what all of that entails today. So this is me. I work for CosmiQ Works, and CosmiQ Works really sits at that intersection of geospatial and machine learning, specifically computer vision. We do this through a variety of ways, mostly applied research projects. Our parent company is In-Q-Tel. So moving into the RarePlanes, RarePlanes, the data set portion, it ultimately is now the largest openly available data set built to test the value of synthetic data for machine learning applications from an overhead perspective. And this was really a unique collaboration between our lab, CosmiQ, and a company called AI.Reverie, who supplied the synthetic data for this data set. So what AI.Reverie is, just in case you're not familiar with synthetic data for computer vision, synthetic data is really generating obviously synthetic data using different techniques. AI.Reverie relies on the Unreal Engine at its core, so using a gaming engine to do this. And it's really designed to procedurally generate multiple varieties of synthetic data with annotations already pre-baked in. So that's really important because training data is such an expense. And this synthetic data really can be helpful for speeding up your training pipeline and getting valuable data when you need it. Looking at this workflow here as an example, in more of a traditional sense rather than an overhead sense that I'm going to walk us through is how you can apply synthetic data. So in this initial setup here, the model is mistaking all these elephants for sheep or cows. When you add in some of the synthetic data, retrain your models, then what happens? You're actually able to detect these elephants with a greater accuracy. And this really became the foundation for RarePlanes because we wanted to flip this to the overhead space and really investigate the value of synthetic in a new modality, which is that overhead satellite imagery geospatial arena. So to do this, we really wanted a data set to examine the value of synthetic, and we curated this with 2 ultimate companies here. So the top company is called Maxar. They are a satellite image provider. And this is from their WorldView-3 sensor, which is the highest resolution sensor commercially available right now. So we curated a very large data set complete with annotations, hand annotations of aircraft. And then we built a similar synthetic data set with the AI.Reverie engine here on the bottom 2 rows. And you can see really the synthetic data is very realistic. The unique thing about this simulator is you can simulate a variety of weather conditions. So you can see different things here like the clouds and the haze, as well as be able to change the backgrounds, add in snow or make the planes sit on grass, really to improve the diversity of your data sets and also increase potentially the generalizability of your models to new locations. So in terms of an outline about what I'll be talking about fully is the dataset overview. This dataset is actually openly available, so you can download it today. How we labeled that dataset, as well as some benchmarks and experimental results. So benchmarks really focus on rare object detection, and that's where really the rare and RarePlanes comes from. So if you have limited training data examples, can you boost with synthetic data, and can that help you improve your results? And then I'll share some resources about where you can download and work with this data set. So in terms of locations, we ended up with 253 unique satellite images here across 112 locations in 22 countries. We really tried to diversify, and we did a stratified random sample across different climate zones to try to maximize that geographic diversity, which can be very important for training models that you would like to generalize to new areas. So ultimately, the real data set has 14,000 aircraft, almost 15,000 with 10 attributes. I'll talk about what those attributes are. and it spans over 2,000 square kilometers. The synthetic portion is much larger. It features 50,000 synthetic images across 15 locations. And if you're wondering about the dots here, the blue ones are going to be our real locations, the red being the synthetic simulated areas, and over 600,000 aircraft labeled here, again, with the same 10 attributes as in the real data set, over 9,000 total square kilometers of simulated area included here. And as I said, this is hosted via the AWS Open Data Program. So you can go in there, download this today. And it's right on that S3 link there. So as long as you have an AWS account and the command line configured, you can pull all of this down for free. And I'll be sharing some more resources so you can learn how to do that at the end of the presentation here. As I stated previously, we're really trying to maximize that geographic diversity with different types of snow, different backgrounds, different look angles. If you look at this top right image here, you can see really a slightly off nadir look angle here. And this is just some of the complexities that are inherent when you're trying to analyze satellite imagery. And it can be a real challenge to have build models that can work well in diverse conditions. So that was really the point of this, trying to maximize that and hope that this would aid in our ability to detect different types of aircraft in this case. So we chose a very unique label taxonomy for this data set. And the reason for that was we really wanted to build something that would have lots of different attributes that you could ultimately tie together to maybe figure out what the type of aircraft it is that you're labeling. So we chose this diamond style because it enables you really to pull out two very important characteristics that can be used to define what an aircraft type is. And that's the wingspan and the length of the plane. So if you measure from the second node here to the final node, that will give you your wingspan. If you measure from the first node measured here to the back end, that will give you the length of your aircraft. And you can pull that out in actual meters as all of this data is georeferenced. Beyond that, we have a number of other characteristics that I'll talk a little bit about. But the important thing with these characteristics is that each of these can be assigned to an aircraft, and you can then train a model to pull out the different types of these characteristics. So if you want to learn about find different aircraft with different types of wing shapes or wing positions, or measure the type of propulsion, that's certainly possible with this data set. And this is really a hierarchical overview of our full taxonomy here. Really showing how we ended up labeling this and the full diversity in the data set. And it's important to understand that you can actually build custom classes with this as well. So if you wanted to measure or find planes with different types of engines or different types of propulsion, or combine any or all of these together, that will ultimately enable you to build these custom classes and then create basically your own unique data set for your own purposes. Which can be certainly much more challenging than just finding single attributes. So beyond the diamond annotations, we also provide bounding boxes, of course, for training object detection models. And then in the synthetic data, we offer full instance segmentation as well to go even a little bit deeper. These two, the bounding box and the diamond, are available both for the synthetic and the real data. So some of the basic detection tasks here, this is, I believe, YOLO V3 that's been trained on this data set. So here we're pulling out aircraft roll. So in this case, if they are large, small, or medium-sized civil transport aircraft. Simpler aircraft detection is also possible. A lot of the models we trained performed very well for these tasks with recall rates around 98%. So that's really nearing human levels, which is encouraging for this. Impressive results so far. And this is an example that we did this past summer, showing how you can ultimately detect the propulsion and the number of engines of different types of planes. So again, this was where we combined these two classes together, and then you're able to detect with fairly high accuracy, again, the propulsion types and the number of engines for these different types of planes. And This is color coded, so you can check this out on the right-hand side here if you trying to figure out what the color scheme means here. So looking at some of the results for that number of engines and propulsion type, we can see here that this is an F1 score for each of these classes. On our y-axis, on our x-axis, we have basically a description of these aircraft. And you can really see here how this is the performance is typically linked with the number of training examples that you have. You can see that when we have this very rare class where we've got 3 engines with jet propulsion, that really only happens 43 times in the data set. And as a result, we end up with this much lower F1 score. And then you can see other types here that are much higher. And we're able to do this very well with modern object detection architectures. So this result here really inspires us to try to investigate the value of synthetic data, and if we can boost and augment our real training data with synthetic and how that might work. So we did some experiments on this. This is the first training scheme we used. It was a very traditional transfer learning approach where we train on basically a large repository of synthetic examples. Train on that for about a quarter to a third of the total training time. Much longer than that, it would actually start to harm your model performance. And then we will train on the full real data set. And so this is the traditional approach for working with synthetic data. And what we found here was that it was quite effective. So looking at these performance metrics here, the blue bar is if we train on the full real data set. The red bar here is if we train on the synthetic data set only. And then the yellow bar here is if we train on just a small subset, so 10% of our real data and the full synthetic data set. And ultimately, what we can see here is that even with just 10% real data augmenting with the synthetic, it performs at really nearly equivalent rates here. So just slightly lower performances. Versus training on the full real data set alone. So this is important, as the implication here really is that you can replace your real data with synthetic and have very minimal performance declines. So moving into this rare object detection overview. So why is rare object detection important? So it's particularly important in the overhead domain, as you can never really guarantee when a satellite image comes over that you're actually able to have your objects of interest included in that collection. So say we wanted to find some Beechcraft starships. So there's presently only 6 active in the world. A few of them actually appear in the RarePlanes data set. And we want to build an object detection model to find these. So this is a particularly challenging task because there's only a couple of these in the world, and building a representative training data set for this will be nearly impossible. So can we augment with synthetic data, and does that help us improve our performance for detecting these objects or really any other type of object? This is just one example, but you could think of this applying to any other domain in the computer vision space where you might have limited training data examples. So this is our first performance metric here, where we're looking at the y-axis here, our mean F1 score. On the x-axis here, this is the number of training examples for each object. And in this case, we're just looking at real data only. So you can see that when we have, again, 10 or fewer training data examples, performance is around 0.05. So ultimately a very terrible result there. And as we gradually add more, obviously performance increases until it really starts to peak around 0.65 for this is an aggregate of multiple classes together. So can we leverage synthetic data in such a way to try to boost that performance? So this was a bit of a different training scheme we used, subtly different, but here we train on our real data for maximum performance. And then we train on just our classes of interest that we want to boost our performance in. So really doing some fine tuning here, just training on those classes of interest. And then we finally train again on a portion of our real data set that again features just some of those examples of our classes of interest. So really just a quick training here. And this technique is valuable because it doesn't require as much synthetic data. It still requires the full real data set, but it ends up being quite effective for this task of really boosting rare object detection performance. And it ends up being pretty much a very lightweight augmentation. So this was that same graph from a few slides ago now, but now we're testing performance with when we add in this synthetic data. And interestingly enough, you can see that we have a very strong performance boost here for our object detection metric when we're adding in the synthetic. So performance ultimately increases from 0.05 to around 0.35. And again, you start to see slightly diminishing returns as you add that synthetic data in. Ultimately, it adds a small boost here in the 30 or less training data examples, but gradually starts to decline as you get more and more prevalent training examples here. So in terms of resources here, I do want to point out a few of these. So the code base that we created in coordination with AI.Reverie is hosted on GitHub. And this is really a pre-processing code base so that you can start to get started. Working with geospatial data can be particularly challenging if you're not used to it. So this is a way to bridge that gap and get you started and be able to modify the GeoJSONs, so the geospatial data, to be able to work with modern computer vision techniques and load your data, and also create custom classes. We have a full user guide here on our website, cosmicworks.org/rareplanes. That also links to a paper that was just accepted to WACV 2021. So that's the Winter Applications of Computer Vision Conference. And that will be published, I believe, in January. There's also a copy of that on archive right now. And again, you can read that right here. The RarePlanes data set on S3, again, this is in the S3 bucket. So it's going to be at this S3 address, rareplanes-public, if you wanted to download it today. And these are our two respective organizations here. So AI.Reverie, again, they provided all the synthetic data for this study. And then CosmiQ Works, which is, again, who I work for. So with that, I will open it up to questions. Again, I'm Jake Shermeyer. Thanks so much for your attention. Appreciate it.
Thank you, Jake. We actually have a coffee break coming up. So this session will reconvene in about 15 minutes. So on the quarter hour, depending on your time zone. I see there aren't any questions in the chat for Jake, so I'm gonna put forth one. Okay. Since you were using transfer learning to basically leverage either the synthetic data or the real data for the airplane category or categories, do you think you could repurpose this same technique for other types of objects that one can identify from like satellite imagery? And have you done that yet in your research?
Yeah, so I mean, I think the key characteristic there is having open data or any data available to do that, which is certainly a real challenge. And one of the motivators for us putting out data sets like this, another initiative we sponsor, is SpaceNet, which my colleague Adam Van Etten, who speaks next, is actually going to talk about some of the work he's done with that. But yeah, in short, no, we really haven't tried these techniques at least for when we're incorporating synthetic data, that is, for any other data sets. But we have tried it for numerous different tasks here. So if it can boost just generic aircraft detection, or say you're trying to identify the role of aircraft or the number of engines of propulsion, it's helpful in those settings that we've experimented with.
Cool, thank you.
Absolutely.
A round of applause. I know one of the other speakers earlier today said that they missed the applause from the audience. Yes. And unfortunately, I cannot unmute everyone to provide applause. But,
okay, well thank you. I'm assuming they're applauding very loudly.
Sure, yeah. in their houses.
Yes, yes.
All right. I'll see everyone at the quarter hour.
All right, thanks.